Okay, we'll start with the EMF of a cell. Previous class, just we had a rough idea of that. What do you mean by EMF of a cell? Here we'll go in detail now. What is a cell? How it will work out? Then what are the how to write KVL across a cell? If some internal resistance means what? Terminal voltage means what? Like so. As such, you know. So whenever cell comes, no. So there's a one basic example is what you can take it. In books what happened when they wrote the cell concept, no, at that time this dry cell is not available. What we had is Lackland cell, Daniel cell, they were using. So later part what happened as the technology got improved after 1970s, the dry cells came into picture. Then we are widely using this dry cell only. We are not using the Daniel and Lackland cell, that one. So that's why in the books what happened, all the content is not yet still updated. Still it's some maybe 70 years old. We hardly get a discussion on this dry cell. But still we can take this an example to study. The overall mechanism is same. But the dry cells, the wet cells, the mechanism is same, but the working is also same, but the way what done all your right equations will be a little bit different. Let me consider this one. So these are called as terminals. Means where you are utilizing the cell to connect to external circuit. So that particular point which you are using for external circuit, no, they are called like a terminals. So A and B are called as terminals. I think in the, if you see it's some at this particular point, some gap will be there, no? Or you can say some sort of hole will be there. So these are what we'll be using for the connection. These are called like a terminals. So here afterwards, what is the cell? Inside what pen there'll be material. Some material will be present. This material. So how there'll be flow of charge will take place. So what is the representation? There's a physical one. So the electrical representation of a cell will go like this. This is the EMF of cell. We use symbol like this. Huh? There's a symbol. EMF of a cell. There's the internal resistance. What is this internal resistance? Resistance offered by the material of cell to the flow of charge is what internal resistance. So what is our internal resistance of a cell? So what it is, resistance offered by a material of cell to the flow of charge is called as internal resistance. This one, and this symbol, it is like a called as electromotive or EMF of a cell. Like this one, and VAB is called as terminal voltage. These are the terms which I'll be using frequently here. Okay, how do the working of this cell will take place? So inside the cell, the same diagram. So there's a terminal B, there's a terminal A. Take like this. So here what happened, let's assume a positive charge. So inside what happened, some chemical reaction occurs. Let's take electrochemical cell. So what is the electrochemical cell? The reaction, the chemical reaction will occur, the output will be electrical energy. So chemical reaction occurs. So due to chemical reaction, then an energy is available. That energy what happened will be utilized by the material of cell, and it will exert a force on this positive charge. And so this will be the force exerted by the battery. FB will write it. So from where this force will come, this force will happen, is available due to chemical reaction. Due to chemical reaction, what happen? Energy is available. That because of that energy, what happen? The material of cell will exert a force. So this particular charge now will move from the negative terminal to positive terminal. This will be negative terminal of cell. This is a positive terminal, or the plus sign and minus sign will be indicated. There's a work done by the battery force. So meanwhile, when it is moving here, when it is moving, the battery force will act here like this. What about the resistance offered by the material of cell? So this will be, you can call like a FR. The material here which is present will offer resistance to the flow of charge. There's one basic property, no? This will be, so continuously open as long as chemical reaction is taking place, continuously open, a charge will be shifted, positive charge will be shifted from negative terminal to positive terminal of a cell. So because of this, what happened here, a positive potential is developed at the end A, and a negative potential is developed here. So then, meanwhile, how long this flow of charge will occur? So continuously here, say positive charge is set up here, a negative charge is there. How long this flow of charge will occur? As long as this battery force is greater than the resistive force. Meanwhile, so at one particular instant, so because of this potential open, an electric field is set up capitally. This electrostatic field is set up. This electrostatic field in what direction will exert a force? Will exert a force in this direction, called Fe. Okay, time being this resistance force, I'll take it out. I'll introduce this to later on. What is Fe? As initial open, the moment you construct a cell, there what happen, the chemical reaction will occur. Due to chemical reaction, energy is available. Due to that energy, what happen, the battery will exert a force on the charge. The charge what happen will be shifted from negative to positive terminal. Because of accumulation of positive charge here, this end will be positive. Because of accumulation of negative charge, the NB will be negative. Then as this charge moving, so because of positive charge deposited, you go to electrostatics. Will there be any electrostatic field is set up? This will be like one plate. This will be like one plate. So electrostatic field is set up. Now, a fresh positive charge, when it is moving, will it encounter any force due to electrostatic field? Yes, it will be towards right. Along this accumulation of charges will occur at the ends, as long as the battery force greater than this electric force. Once the battery force becomes equal to electric force, then no more further drift of charges will occur. In that particular instant, then a constant potential difference is set up. Okay, got this? So here I will define a quantity called as the like a EMF. So what is the basic definition? The EMF of a electrode the electromotive force in the brief we write like this, EMF is the energy provided by a cell per coulomb of charge passing through it. It is measured in volts here. So this is what I like it. Work done per coulomb of charge. So what is the go back to electrostatics? Work done per unit charge. How you define any quantity? Potential, no? So therefore, what should be the unit of this EMF? EMF unit will be volt. That's why it has come volt. Negative charge will flow. For our convenience, we'll just take positive charge. It'll be much easier to analyze the problem. Because this, in fact, it's only negative charge which is flowing, not positive charge. I'm making things clear. Since our electrostatics, we all started with unit positive charge, unit test charge. Can you remember? I told you long back, whenever any discussion comes theoretical, we need unit test charge. the unit test charge, what we assumed was positive. But later on in the 19th century, we came to know that there is nothing called like a moment of displacement of positive charge. It's only the electron which undergoes displacement. Then all our concepts we have to change. So for that purpose, I'm just discussing only the displacement of the positive charge. But actually, practically, positive charge, nothing called like a displacement of positive charge. Is only the negative charge. So what do you mean by negative here? The excess of electrons. What do you mean by positive charge here? The deficiency of electrons. Okay, that. But you just think about only now unit test charge. So all our concepts, we should just think about only the unit test charge here. Okay, this one, why the unit should be volt? Work done per unit charge. Work done per unit test charge in moving it from infinity to that point slowly is called as a potential, no? So therefore, what will be the unit for EMF will become volt. So that this, I'm highlighting it here because of this definition. Okay, now, will there be any potential differences set up as now, will there be further movement of charge as once FB equal to FE, no more movement of charge will occur. No movement of charge occur. How long it will be? As long as what happened, the battery force is balanced electroshift, there won't be any further displacement of charge, and we'll get a constant potential difference. So what is VAB now? The VAB will become equal to applied EMF. So the battery is not connected, no, just left open like that. Fine. So this is the initial part of this one. So when the terminal voltage will become equal to applied EMF, when the cell is not connected to any external circuit, then the terminal voltage will become equal to applied EMF. So when I go and when I measure this terminal voltage, it is equal to the applied EMF. Okay, now let's connect some external circuit. We are discussing first ideal battery. Later on, I'll introduce the non-ideal battery. And there's a terminal A, there's a terminal B. I will connect a bulb or some wire. Your wish, anything you can take it. Some electric energy which will dissipate some electrical energy that should be connected. Now what will happen? So chemical reaction occurs. The story you have to begin like this. Here chemical reaction occurs. Due to chemical reaction, no, a positive charge, what we assume. So that positive charge, what happen, the battery force, what happen, will displace the positive charge from negative terminal to positive terminal. This one. So as this charge starts moving, so when it is available here, so that would happen here VA greater than VB, no? And there's a path, there's a wire. So if you leave a charge, the charge will happen. The positive charge wants to move from higher to lower potential. So this particular positive charge, now it starts moving. No, some sort of electromotive force. So here, what is work done by this particular force here? So come for this one, work done by the cell in moving a charge, work done by the cell, or battery force you can put it, work done by cell in moving a charge from A to B, so B to A. Any formula, this should be equal to charge into VA minus VB. And look at this force. So what all this battery force, what we call, it's an external force. It is an external force, similar to, it's not an electrostatic force. It's an external force or not an electric force, I'll write it. Or non-electric force, sorry. It's a non-electric force. You know electrochemistry. From there is what I am bringing all this concept. So this particular energy, now what it will do? Now the charge, what happens when the battery displaces charge from negative to positive terminal? This much of work the battery does on the charge. Now the charge is possessing energy equal to how much Q into VA minus VB, as VA greater than VB. This energy what happens? With that energy what happens? This charge particle, the battery lifts or pushes the charge from negative to positive terminal. For that the battery does work. Work done by battery now is available as energy for the charge. With that energy what happens? The charge will pass through a wire. It will encounter a resistance. It will utilize that energy to overcome resistance. And here it will lose that energy in the form of heat. And it will come out. Once energy becomes zero, it will be attracted by negative terminal. This is what happens. So what this battery, continuously, it will again lift the charge. Again, it will energize it. It does work. By the time charge comes here, it will have energy. With that energy, it will go around the circuit here. It will lose that energy in the form of heat to overcome resistance. Again, energy becomes zero, will be attracted. So continuously, what the battery is doing, it is supplying energy to charge. And what the external circuit will do, will take that energy now. And what bulb does, it will convert the energy possessed by charge into heat. And the heat will be converted into the light energy. So like this, what this cell is doing, it is converting its chemical energy into electrical energy. And what this wire does, it will help the charge to flow through it. Then what the bulb does, it will take the energy from the charge particle, convert that into heat, and further the heat is converted into light energy. So this mechanism continues. Along this will continue as long as chemical reaction occurs. You know that for the chemical reaction to continuously occur, so there should be like the products also like the reactants must be there. So like this, will there be any lifespan for this cell? Yes, it will be there. So that's why you buy any dry cell. Will it work out for infinite time? No. Why after some days it will stop working? Why the cell will not work out? Because there won't be any fuel left over. There won't be any fuel left over inside the cell where the reaction will occur. Once the fuel gets over, no more reaction. No more reaction means no question of work done by the cell. No question of work done by the cell. No energy for the charge. So no question of heat or say like a electrical power supplied to the bulb. This was the mechanism it occurs here. Got this now? So work done by the cell is what now nothing but will be available as energy, and that is converted as heat across the bulb. Okay, now you see that one. There is a moment of positive charge across cell. No, the material of cell will offer resistance. So this resistance will introduce here. To the flow of charge, or upon this charge, in fact, we cannot move in a path which I shown. It has to overcome the resistance. So how the path of this particular, it will be slightly like this. Why do this zigzag path? Because the material will offer the resistance, sir, but the chemical liquid, even the liquid will offer resistance. When a molecule is moving, it will encounter collisions with adjacent molecules. So because of that, when the charge particle will experience a resistance. So this resistance is what we'll call it as, I'll just indicate FR here. So what is FR? The resistance force offered by the material to the charge particle. That everything what happen will represent by internal resistance of a cell. So here afterwards, now practically how do this circuit will appear? The circuit will appear like this. This is a practical circuit. This is B, this is A. This is what the bulb you have to show like this. This is the practical, and this is what the EMF. Now a current I will flow. The current I will flow. So according to the convention, positive, this should be negative. This should be positive, negative. Let's write the equation now. Let's write KVL. Uh, I'll write KVL plus E minus IR minus I into R equal to 0. So what is current I is equal to E by R plus small r. Let's write the terminal voltage VA minus E plus IR minus VB equals 0. So what is VAB equal to? E minus IR. Okay, look at now. Which voltage will be available for you? Only VAB is what available for the bulb. This is a bulb. If the battery is ideal, if the cell is ideal, then R will be 0. This is a practical one. So tell me like what is the power dissipated across the bulb? Let's go for power, electric power dissipated across bulb. Tell me what is the equation you write it. Power dissipated across bulb should be equal to I square R capital R. What is I is equal to? This should be E by R plus R. Because of internal resistance, no? There is some energy, say, what all earlier in case of ideal, the work done by the cell, there was no any opposition for the flow of charge. Practically, there opposition occurred. A part of energy, a part of work done by cell should be utilized to overcome that resistance. To overcome the resistance. So shall I put it, you know enough electrostatics, huh? Just multiply Q. Q into potential difference, you'll get energy, no? So what is Q into E? Work done by the cell. High into R, that is what energy available across the bulb. What is this high into small r, or this high into capital small r? This will be the drop across the resistance of a cell. Into multiply your charge. So some work is done to overcome this internal resistance. Okay, got this? So some work has to be done to overcome this internal resistance. So that's why the potential difference, now the terminal voltage will be less than applied EMF according to the KVL. Okay, come for this. You look at the power dissipated across the bulb. It's not equal to power generated by the cell. What is the power generated by the cell? Power, electric power generated by a cell. How much it is equal to? E into I. So which is equal to, this is then power dissipated by cell. Power dissipated by a cell. That will be internal resistance. So this we should write I square R. Check it now. Is it all power generated by cell? Will it be given to the bulb? The answer is no. Definitely the answer is no. A part of power what happened? Here what happened? The power generated by cell. A part of it given to the bulb. A part is taken by the resistance only. This is lost as heat. Lost as heat. This is an unwanted one. With this one, so now what happened? If internal resistance is more, then what happened? The particular cell is what happened is of not good quality. So what the cell will do, what all power generated by cell should go to the bulb. But here what is the problem? What all power generated by cell should be available across the bulb. Because of internal resistance happen, some power will be lost here. So shall we call efficiency? What do you mean by efficiency? What do you mean by efficiency? Power dissipated across the bulb by power generated by the cell. So what is the power